charge, but you have in the normal electrical thing, you have 220 volt difference between the tips, and therefore and then you define the electron volt to be the energy that one elementary charge gets by running through a potential of 1 volt. And then a tera electron volt, a TeV, is 10 to the 12 times as much. So it would correspond to this. But even this tera electron volt is still some sort of a little, very small insect energy. It is not a big energy on, well, it's in a way big for a single particle, because it is like an energy of a small insect, but it's not at all a big energy from a human scale. And therefore it is a great achievement to achieve that you can give such energies to the accelerator, to the particles. But they still run with a speed less than light. And it might be a good way to get an impression of how high energy, or how high, by thinking about how much does it run after the speed of light. And that's easy to calculate from the formulas of relativity. And I think that now at this LHC accelerator, the situation is so that you can essentially run as fast as the proton lags behind the light. So it is very small, but the accelerators in my study time, well, then you had 19 GeV protons or so. GeV is 10 to the 9 instead of 10 to the 12 electron volt. And there, it would have been impossible for any means of transportation, jet planes or anything, to follow the difference between them. There was too big difference in it. But now we have this. And I can also show a little picture from there. It is put onto the earth, and actually I once couldn't answer the question of why they were putting it onto the earth, this machine. But I think that some of the experimentalists knew, oh, this is to avoid, I mean, if you would put it, I think there are several reasons. But one thing is also that if you would put it in the Earth's surface, then you would have to expropriate all the houses and the various things you would find on the Earth. It's much easier if you go 150 to 50 meters under Earth. You don't have to ask anybody. You just dig along peacefully, and people don't notice that they are being, that you have a big accelerator with radioactivity and everything deep under your garden. So, and this is like some sort of metro tunnel here. You can see that there is a little roof. There's even a man standing there to give the size, and he has a little dracene. He can go around, you can bicycle, you can walk there, and so on. And there are lots of tourists coming down to see it. And not now, because now the machine is running, and it's not allowed for anybody to go there. But inside these so-called dipoles, these blue tubes there are two holes where one has pumped out the air so that there is free passage, nothing to hit if there is a proton going through. It's not so easy to extract the air completely. But this has been done very well in these tunnels. And I once had at CERN a little lunch with Danes to meet each other, and And one of them I asked, what are you doing? And he said, I'm doing nothing. Because what he was doing was to make this empty space inside the tunnel to get the last air out. But even after you have gotten out the last air, then it is still only competing with what you have in the solar system, but not what you have of emptiness out away from the stars. If you go sufficiently far away from the stars, it will be so empty that that even the people who makes this nothing can compete with it. But anyway, this is good enough. It is not a great problem. Sometimes the protons will of course hit some of the remaining gas, but you can arrange that they hit each other so that it is quite effectively to do it. You somehow have to hit it by having some cross regions, which I have symbolically drawn here, where you let the two highways here, or two passes, where they run in one way and the other, go into the same, and then they hit each other. If you even try to arrange them to hit as much as possible, and then around it you put up a lot of instruments to see what comes out of these collisions. And this is the main purpose of this accelerator, that you want to investigate all the small pieces, in quotation mark, coming out of these collisions of the protons with each other. And from that you want to study what comes out. And sometimes comes out something which you can interpret, this was a Higgs particle. But it's extremely seldom you get the Higgs particle. So you have a great problem. Mostly you get out a type of particles called hadrons, which are particles built from quarks and kept together by gluons. And now I think I should remind you what we are built from, because otherwise you might not. So I think you know, but you should have in mind, of course, that the physicists are, especially the high energy physicists like myself, are working with what is sort of the very smallest bits of particles inside us. So you should know that if you have some water or something, then this consists of some water molecules, for instance, but you have many other molecules and so on. And they consist of 2 hydrogen and 1 oxygen, and these are atoms. And the atom consists of 1 nucleus and some electrons going around. And they go around in elliptic orbits. Well, really they don't go around in elliptic orbits. If we shall describe it in the terms of modern quantum mechanics, then we have to say that they are in a mysterious way almost all over in the atom, that they are in a superposition of being in different places inside the atom, and even in principle almost superposition of being anywhere. Now, superposition, that's a word that is only understandable in the quantum mechanics in this meaning. So it is, well, if one has not learned quantum mechanics, one shouldn't understand it, because it is impossible. And if one has learned quantum mechanics, then one will know that this is a normal situation, that particles are in superposition of being in different places at the same time. This sounds very crazy, and I think this is one of the ways to see that quantum mechanics is on the surface almost self-contradictory. And I could talk, especially if you ask, about discussions by Bohr and Einstein about this consistency of this theory of quantum mechanics. Now perhaps now I'm entering quantum mechanics, I have perhaps even to give you a slide, at least a formal thing. What should you think about with quantum mechanics? And you might think about light. Then historically, Newton would say that light was particles, and Huygens would say that it is waves. And by Maxwell's theory of electrodynamics, it got sort of explained what type of waves it was. So one would perhaps think it was waves that was the right idea. But then by Planck and Einstein and others, one was getting to that actually the light came in small packets, small quanta. So it was perhaps a kind of particles anyway. So I think what one shall say is that contrary to what you would say, okay, either it should be Einstein, it should be Newton is right or Huygens is right, but this is something we should settle. Both ideas might be good, but which one is right, we should get settled. In a way, quantum mechanics says they are both right. It is both particles and waves. And since particles and waves are not at all the same, as you can see, if I draw on a line, sits here a particle, and if I draw some wave, well, it's not the same at all mathematically. So waves and particles are not at all the same. So therefore, to postulate as your physical theory that two objects which are mathematically contradictory should be the same, you are immediately in a danger that your theory will be very inconsistent with itself. And it is not so mysterious if Einstein would come and complain that it is a very bad theory, even if he got Nobel Prize himself for developing it. So this is a bad theory from that point of view. But now you shouldn't believe that that quantum mechanics is at all a bad theory. It's exceedingly good, and all the experiments have supported it even in the most ingenious attempts to tell that it is contradictory and show that it is wrong. Experiment supported it. Quantum mechanics won according to the decision of the experimental results. So it is so in spite of its trouble, it is there. And Bohr has discussed that and said that in some way we have two different pictures giving the same description of reality and so on, and that this is his that you have to live with the two different descriptions even if they are a bit contradictory. But I was just on the way down here. And at this atomic level, we somehow met the quantum mechanics. Bohr simplified an old model from 1913. You had the particles going in these orbits, but then Bohr had to say that they cannot be in all orbits. But this was improved to this better quantum mechanics where they are in superposition. But now, inside the nucleus, one has found protons and neutrons, and they are lying very close to each other. And protons and neutrons, each of them, is now believed, according to many experiments and so on, to consist of quarks. For instance, a proton consists of two up quarks and one down quark. There are different sorts of quarks, up quarks, down quarks, and they even occur in three different colors, red, blue, and should probably have been yellow, but it doesn't matter because it has nothing to do with color anyway. So you would have that, and then one has some particles now, gluons, which in a complicated way manage to bind them together. And these quarks should really have had a third or two-thirds charges of this elementary quantity of charge I mentioned a little earlier. But you have never found these quarks going free. So then one would say, perhaps, that this is worse for the quark theory, that you never find the quark. But now one has given the quark theory this kind of crutch. The theory didn't quite work. Okay, we say there is a very clever way that the computers understand that makes the quark never come out. And they are always going in small bunches with a balance of color, one of each color of the three types of colors, and so. So in that sense, we have one makes it work. This is confined, one says. It means it is fängsel. It is not allowed to get out, and it would get some policeman with it if it tries to go out. Some other quark or anti-quark or so would get out. So it is working like that. And these particles, which consist of these quarks and are held together in this complicated way by the gluons, these particles are called hadrons. And such particles are the most common that comes out when you collide the proton on the proton. So when you collide one proton on another proton here, then comes out of it some particles here. And these particles has names for many Greek letters, K and phi, and well, K is Latin letter, but anyway. So, and there will be protons, and there will be neutrons, and there will be antiprotons. Every particle has an antiparticle, and these antiparticles have very similar properties but opposite electric charge. And and some particles are their own antiparticles. But in any case, you get hadrons out, and you get mainly hadrons out. But seldomly you get particles which are not hadrons. And now I owe to tell you that there are some particle that is not a hadron, and that would be the electron, for instance. So now at least you can know that you know proton and neutron and pi mesons, there are three of them, as examples of hadrons, and then you have an example of a non-hadron would be the electron, and also the light considered as a particle would not be a hadron. So we have some particles which are hadrons and some which are not hadrons. And when you see these collisions with just hadrons, usually they are not so interesting. So you try to forget them and only let the computer take up the data of those events where something else than hadrons comes out, or where the hadrons comes out with very big energies in transverse direction. Then you take them. But normally you try to forget them. So you have to throw away a lot of collisions. So you make so many collisions in this LHC that you cannot afford to write down the data and don't care to write down all what happens. So you only write down when you have an interesting event, which means one with not only hadrons but something else, or with some hadrons coming with very high momenta so that it is interesting. And this is the way you look for it. The Higgs, which was found last year, that was found by photons. But this is actually, it is in this sense the best way to find the Higgs. But it is not the typical thing that happens to a Higgs, that it becomes photons. So the Higgs is normally not becoming photons. The Higgs is, if I call it H, is normally becoming some quarks, B and B bar, which I didn't talk about, but they become hadrons. So that becomes hadrons, which is, there are so many of them in advance that it is very difficult to see those Higgses which produce hadrons, because there are too many in advance. Even of this special type of B, which is much more seldom, but it's not so easy to see. So that means that to see the Higgs, you look for where you had the better chance that it was 2 photons, where it was not hadron. They are more seldom, so it's easier to pick out if there's an interesting Higgs there. Otherwise, it drowns in all the other hadron events. So this was the hard one. Let me see. What were I saying? I was so
can I ask a question?
yes.
This LHC is a large hadron collider, but it's not the hadrons getting, the things collided, it's not the hadron.
Very good question. Yeah, it is, because you see the proton is itself a hadron. You produce hadrons, but the proton is itself the hadron. And it is a sort of strange way that one calls it a hadron collider. It would be like if I was saying, yeah, here is a lot of mammals present listening to me. But there are a lot of mammals present, but they all belong to one special species, unless there's a dog also. So, in the same way, it is actually hadrons that collide in Large Hadron Collider, but it is not, it's only that single species, a proton.
Okay, so the thing that you want to get out of it is the Higgs particle.
Yes, but that you get out whether, whichever hadrons you shoot against, you have a good chance to produce a Higgs.
But this Higgs particle is what the guard in quotation marks is trying to prevent.
Yeah, that is our story, that's right. If our theory was right, then God would prevent that and give this type of accelerators bad luck.
Which happened, right? There was a lot of incidents with the Large Hadron Collider.
That's right! Now you see how we are to rescue our theory. It's very good you ask it, because let me tell what happened. There was an accident, and then there was something with a bird putting some packaging. I think that was the newspapers trying to make more stories out of it, because they wanted to make it more interesting that this machine was starting up. And then they would like to support our theory a little bit by such stories. But there was one accident which was a very important one. And that was that these big things here, they need magnetic fields, because the trick is to make the protons go around, and for that you make a force on them by means of a Lorentz force, it is called, which comes from a magnetic field. When they run across a magnetic field, they get influenced by a force, and they move around in a circle. And this circle is very big, because they move with an enormous speed, so that they're almost a light speed. You remember I said that I could run the rest somehow. And therefore, even with rather strong magnetic fields, they can go around. The purpose of having them going around in the magnetic field That is that you want to keep them so that you can put small electric fields on them and speed them up. Because it's not realistic to speed them up by just putting them through an electric field with 10 to the 12 volt, because that you cannot have in such conditions. This is almost hopeless. This would give a lot of sparks and not work. So you have to keep them to run many times, and then you can speed them up. But then you want to make your magnetic fields as strong as possible, and the stronger, the higher energy you want the particles to have. So the plan was then that you should go up to 7 TeV, towards 7 TeV, that one proton comes with 7 TeV and the other with 7 TeV, and they collide. And for doing that, you would need very strong magnets. Now, these magnets are made by superconducting material, so the current has essentially no resistance. So it is not wasted much energy to the resistance, but you waste a lot of energy to cool it down, because you need to keep them at 2 degrees Kelvin, which is minus 271 or so degrees Celsius. So you have to cool them down and use a lot of energy for that. And then there is a little technical trouble, that these superconducting materials are not so easy to glue together. There will always be a tiny little resistance where they glue together. And if this resistance becomes too big, then you risk that there comes too much heat production anyway, and it may heat it up, and it may no longer be superconducting, and you have fluid helium to cool it down, and it boils with temperatures of this order of magnitude of 2 Kelvin also. So it's very bad for the whole thing if you heat it up. And if this happens too much, you may boil over, and the whole thing, your insurance, your safety systems may work, but not enough, and you can get into trouble. And that happens. So there was too much resistance from the one to the other, and that caused the problem. And that problem would of course be smaller if you go with smaller current. And smaller current means smaller energy of the particles. So one decided to run rather long with only half the energy, so as to avoid these small troubles, because it took a year to build up from the problem. But now the plan is that one will start up and do it with the big one. One will bring the machine down, and then one will very carefully check that you don't have too high resistance or other troubles, and then you will start up. And then when you get to higher energy, you will also produce a bit more Higgses. So now you see how we could rescue our study. We could say, when you now, it was actually our God, in quotation mark, that scared the physicists to run at the lower energy where you don't produce so many Higgses again. So okay, let's go with that. But when you get big amount of Higgses, the next, then he knows that there's a little crisis in space or something like that, and that something bad will happen. And he has this knowledge because he's of course well knowing the future, because it's the influence of the future really, so he knows everything, and Candice, he knows that it will happen. And it's important for our hopes for the theory. I didn't yet mention that there was a machine in Texas called SSC. And this machine in Texas was killed by the Congress before it ever got started. But one had made about 1/4 of the tunnel, and it should have been somewhat bigger than LHC, but in many respects similar to LHC. So in that way, it would have been bigger, and produced a lot of Higgses, but it never